In this lesson, I'm going to go over discrete, continuous, and discontinuous functions. So a discrete relationship is a relationship that is made up of separate points. A nice way to remember a discrete function, or to even imagine it visually, is if you were to make a graph of a discrete function, you would have to pick up your pencil. That's kind of the best way to remember whether or not something's discrete. A relationship can also be continuous. So here, all the points are connected. You actually can draw a nice smooth line. When making a graph, or when you make the graph of a continuous function, you never have to pick up your pencil. And this is the example written here. So when you think about discrete and continuous, it happens with different types of events. So I'm wondering, what are some examples of discrete and continuous events you could imagine? I want you to take a minute to think of some on your own. Just pause the video. And then after that, kind of replay it and see if you came up with something similar to what I'm thinking. So some of the events I can imagine for discrete, or some examples, would be, for example, turning on a light switch so it's either on or off. So that's an example of a discrete event. Another example of a discrete event would be my shoe size, like what size shoes I'm wearing. And that's because each time I go to a shoe store, I would have to pick up a different size. I can't, like, my shoes aren't going to expand to every length in between. I'm either a 7.5, 8.5. I have to buy what they have. So that's an example, a couple of examples of discrete events I can imagine. It could also be with clothes size as well. Like, I can't get every size in between. I'm either, a 4, 5, 6, 7, 8. Well, I think we kind of skipped some only even numbers when you're an adult. But, I had to pick a number, 9, up to whatever they go to. But I have to pick one size. I can't get like a infinite number of size. I can't be 8 3/4. Continuous events are events that are constantly happening, or you can get every value in between. For example, my height. I started off at a certain height, usually around, I forgot, maybe about 2 feet. I forget how, maybe probably less than that, 18 inches or so. And then as I get bigger and bigger, up until when I reach my current size, I did hit every value in between. Although sometimes to parents, it doesn't feel that way. It feels like you're sprouting up overnight, but you do hit every value in between. Another example of a continuous event will be like filling a cup of water, right? You slowly increase the levels. Like if I'm doing it from a faucet, that would be an example of a continuous event. Other examples could be like all kinds of things, age, like almost anything that changes with time. You slowly change. So if I were to graph my age, I could draw that graph with a pencil without picking that pencil up off of a paper. So we spoke about discrete versus continuous, but what is this discontinuous? What does that mean? So a relation is discontinuous if it does not vary continuously as the variable increases for certain values, or between certain values of the variable. With a discontinuous function, you're usually able to graph part of the function without picking up your pencil, but at some point you're going to have to pick up your pencil because the value at a given point, so you're thinking the x value, it's a little different. Like it doesn't quite follow the rules that the rest of the graph was following. So this can happen in two different ways. We can have either an essential discontinuity or a removable discontinuity. And I think one of the best ways to demonstrate this is just to go to the next slide where I have actual examples. So you can have an infinite discontinuity, and an example is right here. So you imagine this right here is a point of interest on our x-axis, but you notice that as we get closer and closer from the right, so as we approach this x value from the right, the function here, it shoots off to positive infinity, and as we approach this function from the left, this function starts to shoot off to negative infinity. So here we say there's no limit. So when we think about a limit is defined to be the value, the y value that we get as we approach the the value or x value from the right and from the left. Ideally, in a continuous function, it tends to be the same number. So like if we think of like a point right here, as we approach from the right and from the left, we're going to actually start to get the same y value. But here, because it's split and we have a vertical asymptote right here, or infinite discontinuity, there is no limit. We're getting two completely different things. And here, and this is an example of an essential, let me just put this here, because these are both of these are essential discontinuities. Here is a different type of essential discontinuity. We call it a jump discontinuity. And you notice that as you're traveling from the right and you keep going, you actually have to jump up in order to continue the graph. So, or you could jump up or down, it doesn't matter. But this is also an example of like a piecewise function. So that's why you may have something like this. We studied that in 9th grade. But still, like as you approach this certain value, so imagine this is my x value of interest. As I approach it from the left, I'm going to get one number. As I approach it from the right, I'm going to get a different number. Like here it's going to be negative and here it's going to be positive. So the limit as I approach this value, right, the value I get just before I get there, just before to the right and just to the left are two different numbers. So we say it doesn't exist. So there's no limit right here. The other type of discontinuity we could have is what's known as a removable discontinuity. So with removable discontinuities, there is a limit. So we imagine this point. So for whatever reason, we can't include this point. Maybe this would have made our denominator equal to 0. But as we approach this point to the right, and from the right, and we approach from the left, we're going to find that this is a really big circle. Normally they're tinier, but we're going to actually get the same y value. So the limit does exist. The only thing is, for whatever reason, we have like a hole, or we have to skip over one particular point. So whenever it looks like it's just like a simple break in a graph. So it seems like there's a general rule. We're just missing one point. In those cases, we have what's known as a removable discontinuity. And over here, this is just another example of one that we saw before. Remember, these are essential. So this is an essential discontinuity, but it is it's another jump discontinuity. So here we just kind of went over the two major. So your essential and your removable. So here you're going to do a couple of examples. Notice that I did not give you graphs, but in order to approach this problem thinking of that graph method, you can always attempt to sketch out a graph and then think about what you would get. So here, you need to first determine if it's discrete, continuous, or discontinuous. So remember, discrete versus the others is that discrete, you have to pick up your pencil many times in order to make that graph. Continuous is you can make a graph of that function without ever picking up your pencil. And discontinuous means you can draw parts of the graph without picking up your pencil, but at some point you're going to have to lift it up. So I want you to look at A, B, C, and D. You can even use Desmos as a guide if you want to take a quick peek at how to make these graphs. And when you're all done, I want you to pull out this little answer, kind of check your work.